Okay. All right, so number 1 should be one we already know how to do. Should be. All right. What should the u be in that situation? 2x minus 1. All right, du is 2 dx. All right. We do not have a 2 with our dx, but we can just multiply that dx by 2. What will we have to put out front? 1/2. All right, so if we switch everything to u's, we're going to have 1/2 integral square root of u du. I would rather write this with fractional exponents, so that would be u to the 1/2 du. All right, so if this is the case now, I've got to increase my exponent by 1, so it's going to give me 3/2. I'm going to divide out front by that new exponent, and I'm going to put a plus c over here, and I got to have my 1/2, right? And so that ends up being 1/2 times 2/3 u to the 3/2 plus c. Those 2's right there cancel. We're going to get 1/3 u to the 3/2 plus c, and that is 1/3 2x minus 1 to the 3/2 plus c. And they might write that back as roots. If they do, it's square root of 2x minus 1 to the 3rd power. They may just leave it like it is for that. So we should feel pretty comfortable with that. At this point, are you guys feeling okay doing a problem that looks like that? Okay, we're all right. Okay, now, what if I give you the exact same problem, but I put an x right here? So here's the problem with this, right? Like I still, pretty much the only choice I have for my u in this case is 2x minus 1. And then therefore my du is 2 dx. And so I would still need to multiply by 2 on the inside and a 1/2 on the outside. But here's the problem. When I go to substitute here, right, this part right here is u. This part right here is du. But this is going to give me, I'll have 1/2 integral. This x right here has not been replaced with anything, right? So I've got like x times the square root of u du. And can I integrate something with respect to u when I still have an x in the equation? I cannot. So we've got to do something with that x. But we can't make it part of our du. We cannot pull it out front because it's a variable. If it was a coefficient, if that was a 7, it would be fine. We could just pull it out front, right? We've had some that were like that. But we can't take an x and pull it outside of the integral. Any ideas? What? Can't turn it into a c. All right. I think this is so cool. All right, right here. I know u equals 2x minus 1. Correct? If u equals 2x minus 1, I can find out what x is. I can add 1 to both sides, which will give me u equals 2x. And I can divide by 2 right here. So x is going to equal u plus 1 divided by 2. Now, if x equals u plus 1 divided by 2, what can I do with that? Replace it over here for this x, right? So I'm going to take this, and I'm going to plug it in over here for that x. So I have 1/2 integral of u plus 1 over 2 times the square root of u du. Everything's used now, but it's a little complicated. What 2? The 2 dx gets replaced with the du there. So the 2 is not on the inside anymore. But you do have the 1/2 that's still on the outside. Alright, so we don't know how to integrate that right now because it's got stuff that's multiplied. So we've got to get this stuff turned into something I can use the power rule for. Because pretty much I only know how to do the power rule to integrate, right? But I can do that because I can put this over 1, which means I could multiply the numerator together and the denominator together, which basically means I'm distributing that square root of u, which, remember, square root of u is u to the 1/2, right? So if I'm doing u to the 1/2 and I'm multiplying it by u plus 1, then that is going to give me u to the 3/2 plus u to the 1/2 on the top, and then on the bottom I'll just get a 2, and my du stays over there on the side. I could do love connection, for sure. Or, this really, right here, is 1/2 times u to the 3/2 plus u to the 1/2 du. Okay, here. Because that dividing the whole thing by 2 is the same as multiplying the whole thing by 1/2. And what can I do with that 1/2? It can go out front because it's just a coefficient. So I can take this and pull it out here and put it with that other 1/2 that's already there. So that will give me 1/4 integral of u to the 3/2 plus u to the 1/2 du. Now we've got it to something we can work with, right? You do want to be careful here. That 1/4 needs to stay out front, and you need to have brackets because it's going to have to get distributed to both things. We're going to increase our exponent by 1, which will give us 5/2 here. And then we got to divide out front by 5/2, which is going to be 2/5 if you want to skip ahead of me there. And then over here we got u to the 3/2, and we got to divide out front by 3/2. And then we will have a plus c on the end. Does it matter if the plus c is inside or outside of those brackets? It really doesn't, because if it's on the inside of the brackets, the 1/4 gets distributed to it. But what is 1/4 of an unknown value? It's still just an unknown value, right? So a c, like if you're distributing to that c, you don't really have to write it down because it just sort of absorbs anything that happens to it. So this is going to be 1/4 times 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus c. And so that is going to give me, when I do 1/4 times 2/5, that will give me 2/20, so 1/10. And I'm going to go ahead and put my u back in, which was 2x minus 1. 2x minus 1 to the 5/2. And then 1/4 times 2/3 is going to give me 2 over 12, which is 1/6. 2x minus 1. 2 3/2. And I got the plus c on the end here. And there's always a chance they go back to roots or something there. Probably they're just going to leave it like this on that. It can go either place. Alright, so these are definitely more difficult because you end up with this like extra stuff you can't replace, and you've got to adjust that, and then it makes it a more difficult integral as well. But I think they're so cool. Like I very much appreciate this algebra right here. I think it's kind of cool that we can do it.
I really don't like
That X out there, yeah. It was so easy the first time without the X, wasn't it?
Yeah.
Like we've gotten so good, that first one feels kind of easy now, hopefully. At least like doable. And then they throw that X there and look what happens. Yeah. Alright, let's try another one. Actually, hold on. Hold on. I think I've thrown this in here and it's not even, it doesn't even go in this section.
Dude, this is like the fourth. This is like that fourth time.
I do need to revise a couple things. I apologize. All right, this is a fine problem, but does it have anything extra, like an extra X somewhere? What would you use for your U? No. Sine of 3x. Because sine is being raised to the second power. And, I don't know, maybe we do need to do it. Alright, this one really doesn't go in this section, but I don't think it's going to hurt us to do it. It might. Alright, so U for this one is going to be sine of 3x. What is du going to be? Nope. Cosine of 3x, not over 3, times 3 with a dx over here. Okay, so we almost have our du. We just need a 3 with it. So we got to multiply by 1/3 out front. So this stuff right here is my u. It's being squared. And then this stuff right here is my du. The reason we need to use sine here instead of cosine is because sine is being squared. So if we do it the other way around, the derivative of cosine is sine, but it won't be squared. So we won't be able to deal with that. All right, so if we switch to u's, we've got 1/3. We've just got u to the second du. We are going to integrate. That will be u to the third power. We already have a 1/3 out here. We got to divide by the 3 here, so we'll get another 1/3. We'll put our plus c. So we get 1/9 u to the third plus c. And u is sine of 3x. So we'll do 1/9 sine of 3x cubed plus c. And they will probably write it this way. They'll probably put that cube right there for your sine of 3x plus c. I don't know. This last one's going to be a little longer, Jeremy. Well, does it count if you use the back side of the paper? Oh, okay. It'll be fine.
I could have taken it back. It's like you can do it. It's just like a game.
All right.
It's like playing Madden.
Questions on that? This one doesn't really belong in this section. It didn't have anything extra. It could have been in the other sections. I don't really know why I decided to throw it in here, but I did. But it's good practice because I think we were a little shaky on what to do with that one. So.
When I see trig, I skip it and go to the next one.
Yeah, trig is like,
The trig is bad for this though. It's just something.
Yeah, it's not. The trig is not. Some of the trig problems are easier than the other problems, especially if they're just like sine and cosine ones. So don't be so scared. Don't have a phobia of a trig phobia.
If I see like a cotangent and a secant, yeah, I would skip that.
I mean, yeah.
See.
Yeah. I don't love them. I honestly also have, like, I strongly question why cotangent would ever be useful in the real world anyway. Why don't we just use tangent instead? It's just the reciprocal. I don't know.
I'd rather do this than optimization and related rates.
Yeah. You definitely don't have to think about context. It's process on this. Yeah. I would argue that, like, it's easier to teach this because since it is a process, like, I can tell you where you went wrong versus having to try to explain what you're visualizing in your head. That's hard to teach. All right. Okay. What do you guys think for the U? It's going to have to be 3x plus 2. So that would make du just 3 dx. So we're running into the same issue we had on that first or the second problem that we did, right? I can put a 3 right here. That's no problem. I'll put a 1/3 out front. So there is my du. But this x on top right here can't be there, right? It's got to be replaced. So what are we going to do? We're going to solve for x in that u statement, right? So I've got u equals 3x plus 2. I'll need to subtract 2 from both sides. U minus 2 equals 3x. And I'll divide by 3. So u minus 2 over 3 equals x. Oh boy. I have a feeling I'm not going to like this once I plug it in. Alright. Here we go. We're on the top. We've got u minus 2 over 3. In the bottom, right there's my u. So I've got square root of u. And I've got du over here to the side. Little fractions inside of fractions. That's a nightmare, right? Okay, we definitely aren't going to be able to get anywhere with complex fractions. We can't have fractions inside of fractions. So let's make this one a fraction. And how do I deal with dividing fractions?
Well, you get 5.
It's easy as pie. Flip the second and multiply. So u minus 2 over 3 times 1 over the square root of u du, which, if I put that together, is going to be u minus 2 over 3 square root of u du. It looks better than it did. We still can't take the integral of that, right? Because we only know power rule for taking integrals. So, any ideas? Okay, so it is okay because that 3 right there is just a coefficient. Right there, it is okay to pull that out here because it's just multiplied by that. So it's like pulling out a 1/3, so that'll give us 1/9. And I heard something else over here. What'd you say, Liam? Maybe. Did you say something? Negative exponents, what could we use negative exponents for? U to the negative 1/2, so I could write this as U to the negative 1/2 times U minus 2. And then I could distribute that. The 3, you can leave it there if you want and have it over 3, but it's going to be easier if we pull it. You know, when we move this to the top, the 3 doesn't go with it, so it's just easiest to pull it out front. So I'm going to get U to the positive 1/2 minus 2U to the negative 1/2. And finally, I've got something I actually can integrate. What's another option besides using those negative exponents? You can love connection that also, because you just have one thing on the bottom, so you can do, if you would like there, you could love connection that. Those are both options there. Okay, questions so far? All right, so now we should be at what should hopefully be the easier part of this. This is just power rule right here. 1/9 is going to stay out front. Make sure you got a bracket because you got more than one thing on the inside this time. You're going to do U to the 3/2. And then, is it okay with you guys? 1 divided by 3/2 is going to be 2/3. Is it okay for me to skip that step and just switch it to a 2/3? And then over here, I'm going to get U to the 1/2. And I'll be doing 2 divided by 1/2. What is 2 divided by 1/2? It's 4. And then the C can go on the inside or outside. Doesn't matter. It's easier if you just leave it on the outside. And so we can distribute that 1/9. It's going to give us 2 over 27. Let's go ahead and put our x back, our U back in there. 3x plus 2. 3x plus 2 to the 3/2 minus 4/9 times 3x plus 2 to the 1/2 plus c. Oh wait, this just made me think of something. We might should have known number 2. They might not leave it like this. They might not. They might change it to roots. That's a possibility. Here's something else they might do. Let me just throw this out there. So definitely free response, stop here. So like on an FRQ, stop here. Don't do anything else to this. Alright. They might, these two match right here. They might factor out the lowest exponent there of that. So if they do that, I might need to look back at the first one and see if they do. If they do that, they are taking 3x plus 2 to the 1/2 and they're factoring it out. So they would pull out 3x plus 2 to the 1/2 power. In fact, they would have never distributed that 1/9, but I'm just going to leave it. It'll be fine. So we'll have 2 over 27. What will I get right there? 3x plus 2 to the first power. And then what will I get over here when I pull out that 3x plus 2? What? 12 over 27 reduces to 4/9. So you were correct, but and so they will make that square root of 3x plus 2. And then over here, 2 over 27 times 3. 2 over 27 times 3. That will reduce and make that 9. So you'll get 2/9 x plus 4 over 27 minus, in fact, it actually might be more helpful here to have 12 over 27. Because you got to put those together. So Liam, yeah, he was ahead of his time. So 2 ninths x minus, that's going to give us negative 8 over 27. Like that. Plus C. I'm not sure if they will do this to you, but they might do this to you. Which is terribly frustrating if it's a multiple choice problem and you got all the way to this and you got it right and then you can't find your answer choice there. But there's a chance they'll do it. Maybe. There. Let's look at that. That's beautiful, isn't it? Okay.
This one you can show your.
Yeah, go show your mom and dad. They're gonna be impressed with you. They're gonna be impressed. It's gonna have this happen to it.
We can do it.
Why do you go here? Why do you go here? Why do you go here?
Because we're superior.
Yeah. We get bullied out again. No. I mean, I came here for swimming.
Yeah, we do have a pretty good swimming program.
Friends and academic reasons. That's what I told him. Oh, wait, we don't have to swim anymore. You came here for swim. I came here for swim. I can stay now. I'm done.
All right. Okay. Yeah. Yeah. Okay. Let's look at this problem. Actually, no, we could have done this one already. We could have. We could have. Because u, what does u need to be for this problem? G of x. What was g of x? 5 minus x squared. So I was wrong about this. We could have done this one anyway. Well, it won't hurt to do it now. All right, now, what's the derivative of 5 minus x? Negative 2x dx. So, I do need a negative 2 right here with that x, which means I need a negative 1/2 out front. So, to switch this to our integral, we are going to have, or to our u, we're going to have negative 1/2 integral. This stuff right here, the negative 2x, and with the dx, that's our du. This part right here is our u. So we just have f prime of u du. What do we need to do with our limits? Plug them in. So I have 5 minus 1 squared, which is going to give me 4 right here. And I'll have 5 minus 2 squared, which is going to give me 1. That goes on top, so that makes our limits backwards, right? Since we probably don't want our limits to be backwards, especially in this case, because what do we have to look at to find f prime of u? Graph, right? All we have for f is a graph. We don't have the function. So if you're looking from a graph, you don't want your limits to be backwards. When you're looking at that area above or below the curve, it's always left to right. So we are taking the limits right here, and we are plugging them into this equation. So for 1, we got 5 minus 1 squared, which is going to give us 4. And it goes on the bottom because that limit was on the bottom. And then we take the top number, which was 2, 5 minus 2 squared, and that's going to give us 1. It goes on the top because 2 was on the top. Okay? So if we switch those limits now, though, because we want them to go from lowest number to highest number, that will make this positive 1/2 integral from 1 to 4 f prime of u du. How am I going to find the integral from 1 to 4 of f prime of u du? You just look at the graph. It's the area under the curve, because this graph is f prime, right? Area under the curve from 1 to 4. What is it? It's negative 7. It's from 1 to 4 and not 0 to 4. 0 to 4 would be negative 5. So we got 1/2 times -7, which will give us -7 over 2 for our answer. I was mistaken. That x was not an issue. We did already know how to do it, kind of.
So you didn't have to integrate that.
The reason that you did not have to integrate is because you have the graph of f prime. And whenever you have this right here, that means the area under f prime from 1 to 4. So since you have the graph and you know what that area underneath it is, you don't have to integrate. If you did integrate, Liam, you would get 1/2. Oh, let me switch back to a pen. If you did integrate, which is an option, you'd get 1/2 times f of 4 minus f of 1. And we did find f of 4 and f of 1 back up here in part B, right? F of 4 was 10, f of 1 was 17. So it'd be 1/2 10 minus 17, and you would get the same answer if you did it that way. But it's not really necessary to do it that way since we have the graph of f prime. But yes, yeah, it would, and you'd have like a plus c. You get like an equation as your answer for that because it wouldn't. Yeah, I don't think they'd ask it if it didn't have the limits on it. All right, so we got 20 minutes again.